Today we're going to be deriving the equations for reflection and transmission of incident electromagnetic waves, and then use that to derive what the angle is for total internal reflection. So first, we are going to look at the simplest case of normal incidence. This is when you have a electromagnetic wave propagating exactly normal to your media. So to draw this out, we have our x component pointing upward, a z component, and then a y component that points inward towards the screen. And we have two different media, one which can be described with the parameters epsilon1, mu1, and the other which can be described by the parameters epsilon2, mu2. Now, let us imagine an incident wave propagating in the z direction with an electromagnetic component in the y direction, E sub I, and a magnetic an electromagnetic component pointing upwards in the x direction, and a magnetic field component pointing in the y direction. Then, when this incident wave hits the boundary, it'll produce a transmission wave with similar direction for the magnetic and the electric component, and it'll produce a reflected wave, which has a component E sub r, which points in the same direction as E sub I, but now the wave is propagated is rotated 90 degrees as it propagates, so that h sub r points in the negative y hat direction. So if we were to describe, first we need to describe the incident electric and magnetic fields, which can be described pretty simply as incident of the electric field is equal to E naught e to the minus j beta 1 z, where here beta is equal to omega square root of mu epsilon, and h sub I is equal to E naught over square root of nabla 1, nu 1, where nu can be described as epsilon over mu. And then similarly, we'll have a phasor component e to the minus j beta 1 z, and the e component points in the positive y hat direction, the positive x hat direction, and the h component points in the positive y hat direction. Then, to describe the transmission and the reflected components, we have to look at both direction as well as look at the magnitude, which is affected by the reflection coefficient and the transmission coefficient. So E sub t in this scenario would equal whatever the transmission coefficient is times our E incident expression, which is E naught e to the minus j beta 2 this time, because it's in the second media, times z, still in the x hat direction, as you can see from the diagram that we had previously, and h sub t is equal to t over square root of now nu 2 E naught e to the minus j beta 2 z x hat, or y hat. And then the reflected components will be pretty similar. In this case, I'll edit it. In this case, because it's in media 1 instead of media 2, like with the transmitted cases, we'll have beta 1 and nu 1. And instead of our transmission coefficient, it's our reflection coefficient, which I'll write like this. Now, with, and this is for reflected coefficients. Now, with these equations that we have derived from normal incidence scenario, we can then use the boundary conditions that we know, using Maxwell's equations to derive some further equations that will help us relate gamma to t and relate the reflection coefficient of the and help derive functions for the reflection and the transmission coefficient. So we can say that using Gauss's law, we know that, using Ampere's law, we can say that the closed integral of E dot dl is equal to minus partial b over partial t. But if we make this y length, this z length, really small, approach 0, then this can be simplified to e sub 1 times L minus e sub 2 times L equals 0. And then, where e sub 1 is the tangential component of the e sub 1 field, and e sub 2 is the tangential component of the e sub 2 field. And then, this can be rewritten now using the vectors that we know as e sub I plus e sub r minus e sub t equals 0. And then we can write these in terms of our coefficients as now 1 times E naught plus gamma times E naught is equal to transmission coefficient times E naught. And all the E naughts cancel, giving us this as our first equation, describing the relationship between gamma and T. Next, we can use boundary conditions in the magnetic fields to derive another equation. So using another one of Maxwell's equations, we can say that the H tangential field on the first side minus the H tangential field on the second side equals 0. Plugging in the expressions that we have above, we can then say that, and I should mention that these phasor components will cancel out when we look at these boundary conditions because z equals 0 at the boundary, which is why there's no concern even though beta 1 is not equal to beta 2 here. But anyways, so h sub 1 is h sub t plus h sub r. H sub t is equal to h sub t minus h sub r, since they point in opposite directions. So we can rewrite that as 1 over the square root of nu 1 minus gamma over the square root of mu 1 minus h sub t, which is transmission coefficient, divided by the square root of nu 2. And so this can be rewritten now as 1 minus gamma times the square root of nu 2 is equal to the transmission coefficient times nu 1. And these two equations now give us relationships between gamma and t, which we can now solve as a system to be able to get t and gamma as functions of nu1 and nu2. So we can rewrite this now as 1 plus gamma is equal to 1 minus gamma square root of mu2 over square root of mu1. And then solving for gamma, we get gamma equals mu2 minus mu1 divided by nu2 plus nu1. And then our transmission coefficient is just that, plus 1, using this equation. Now this is the simplest case that we can do. We can solve for where we have normal incidence, but let's look at a more complicated scenario where we have oblique incidence. That is, the electromagnetic wave propagates in a direction that's not perfectly perpendicular to the media or the boundary. So in this case, let's draw it out. We have our x-axis, our z-axis, and our y-axis. So in this case, there's two main types of polarizations we can consider when looking at transmission and reflection in this sense. So first, we will take a look at perpendicular polarization. And I should mention this polarization is basically just describing the direction in which the electric and magnetic fields point. So with perpendicular polarization, the electric field points towards you is the key idea. So if we have our incident with E incident here, and I will write perpendicular, and then our H incident here, perpendicular polarized, then we will have E sub R perpendicular, H sub R perpendicular, and we will have E sub T perpendicular and H sub T perpendicular polarized. With our theta sub T transmission angle, reflection angle, and incident angle. Now the first thing we should do is we should express our incident electric and magnetic fields as phasors. So E sub I perpendicular can be described as E naught e to the minus j beta 1 dotted with r, where r is whatever our position vector is, in the y hat direction. H perpendicular incident is equal to E naught over nu 1 e to the minus j beta 1 dot r, this time in the and you can do the trigonometry out for yourself, but it will be in the minus cosine theta sub I x hat plus sine theta sub I y hat, or sorry, z hat. And then continuing with this, now that we have ways of describing E sub I and H sub I, we now want to be able to describe E sub r, our transmission and our reflection electromagnetic fields. So E sub r perpendicular is equal to gamma times E naught. Oh wait, actually before we jump to that, we should solve this dot product that we've created here. So B sub 1 describes the propagation vector, which we can rewrite as E minus J beta 1, and this vector is, let's see here, it would be cosine theta sub I sine theta sub I, and our position vector is described as dot z comma x, again in the y hat direction. Then E sub I perpendicular can be described as E naught e to the minus j beta 1 z cosine theta sub I minus x sine theta sub I in the y hat direction. Now I'm going to pause for here, leave you on a cliffhanger, because we'll look at what the incident magnetic field is in the next video. Thanks for watching. Make sure to like and subscribe and leave a comment if you have any questions. I'll follow with another part to explain the rest.